Hi, I wanted to try to just do a short video on K values, KAs and KBs. This, I don't know exactly why it's been so confusing, but the KAs and KV values have been a problem for both classes. But remember that when we're doing acid and base chemistry, it's just a continuation of equilibrium. It's equilibrium in a new context. So anytime you see a K value, it doesn't matter whether it's Ka, Kb, Ksp, any of those, it's still an equilibrium constant. So it's all still a products over reactants type of deal. If it's less than 1, then you know that the reactants are favored. If it's greater than 1, you know that the products are favored, just like it has been all the way through equilibrium. The difference is that when we start getting these little indicators, it's just sort of telling us what's going on. So a Ka is referring specifically to an acid dissociation. So like an acid in its ability to be an acid, its ability to dissociate. The Kb value is specifically for a base. So any acid we have, if we have, for instance, acetic acid, you add water to that, well, acetic acid is an acid, so it's a proton donor. So that means on the product side, you're going to get some hydronium and some acetate. Okay? Now, it is at equilibrium, which means it did not dissociate completely like your strong acids do. Therefore, it's at equilibrium. That's why we have the equilibrium arrows. So the higher the Ka value, the stronger the weak acid. So in this case, I believe the Ka value is about 1.8 times 10 to the negative fifth. Right? And that just tells us, oh, okay, so it's an acid, but that's still a lot less than 1. It's a weak acid, and in this case, the reactants are favored. Okay, it's not splitting up all that much. On the other side, Kb is for bases, the ability of something to be a base. Now, acetate is a base itself. Okay, so C2H3O2. Okay, this is not, it doesn't have to have that H in front of it. That is something that dissociates as part of the acid, the acidness, I suppose, of acetic acid. That's what makes it an acid. It has that hydrogen to donate. Now that it doesn't have that, this is just acetic acid's conjugate base, and it will act like a base. It will accept a proton. So if you added water to that, now it's going to accept a proton, and it's going to make acetic acid and hydroxide. Now you're like, wait a second, Mr. Dottie, it made acetic acid, so it produced an acid. Well, here's the thing. Acid strength is its ability to make hydronium, right? So do you see any hydronium on the on the right side? Absolutely not. It's not dissociated. So it did, however, make hydroxide, and that's our base indicator, if you will. We'll talk about real indicators later. So in this case, acetate is acting like the base. So we want to find the Kb value. We want to find the equilibrium constant for this equation. Well, how do we do that? Well, acid-base conjugate pairs, they kind of go together. If you take the acid part and get its Ka value, and then you have the base part and you get its Kb value, and you multiply them, it will always equal 1 times 10 to the negative 14th, which is Kw. You'll recognize that from before. This does not mean that acetic acid has a Kb value. It means acetate has a Kb value. The Ka here goes with acetic acid. The Kb value goes with acetate. I hope that makes sense. You're not giving a Ka value to the base. You're not giving a Kb value to the acid. They're the conjugate pairs. So in this case, to solve for Kb, you'll take the Ka value and divide 1 times 10 to the negative 14th by that Ka value. So 1 times 10 to the negative 14th divided by the Ka, which in this case is 1 times 10 to the negative 5th. 1.8 times 10 to the negative 5th. That is going to give you the Kb value. And for acetic acid, I believe it's 5.6 times 10 to the negative 10th. Alright, so I'll get rid of that. That belongs up here. Now, once again, I made a silly, and it's, just so you know, it's not going to the acid. Now here's the thing. What does this mean? Well, this means that in the base equation, it's less than 1. It's a lot less than 1, so this also favors the reactants. In both these situations, the reactants are favored. Acetic acid is not a strong acid. Acetate is not a strong base. And if you compare the Ka value to the Kb value, notice that acetic acid's Ka value is larger than acetate's Kb. That means acetic acid is a stronger acid than acetate is a base. I think that the terminology might be what's confusing people, and just, separate things, try to notice whether it's an acid or a base, and realize that they're two totally separate equations. Once you figure out whether it's an acid or a base, the acid equation is going to produce hydronium. The base equation is not. So just, it might take some practice, but don't get them all messed up as far as trying to assign Kb values to acids and Ka values to bases. They are separate. They go with the conjugates. Anyways, I hope I didn't just make things more complicated, but I wanted to try to clear that up a little, and hopefully